In this unit, we go back to data analysis. We're going to talk specifically about polynomial functions as we do that. But one of the first things we need to look at before analyzing polynomial functions is actually determining what they look like and their characteristics. So what I've done for you is given you two examples of polynomial functions with degree 1. Now, the degree of a function refers to its exponent, and so this first one is f of x equals x plus 1. The exponent on that x is a 1. That's why it's a degree 1. The second one is f of x equals negative 2x minus 1, again with an exponent of 1 on the x to make that degree 1. Degree 1 polynomials form lines. Sometimes, like this first one, the lines move up from left to right. As with the bottom one, they move down left to right. And that is a consequence of what's called the leading coefficient. That is the number that's in front of your degree polynomial. So in f of x equals x plus 1, we have a leading coefficient, and I probably shouldn't draw a circle there. You might get confused as that's a 0. It's not. The leading coefficient in front of that x is a 1. Specifically, it is a positive 1, and that's what causes the function to move up from left to right. In the second one, the leading coefficient is negative 2. Specifically, it's a negative. The negative is what causes it to move down from left to right. So the characteristics, we will always have one x-intercept, we will always have one y-intercept, and the end behavior, which talks about the left and the right ends of the graph, will either go from quadrant 3 to quadrant 1 if we are moving up from left to right, or from quadrant 2 to quadrant 4 if we're moving down left to right. Just remember quadrant numbers 1, 2, 3, and 4. With that, we're going to take a look at degrees 2 and 3. Degree 2 polynomials, these are parabolas. We talked about them extensively in grade 11, in Foundations 20, and also Pre-Calculus 20 if you took it. But degree 2 polynomials will do one of two things. They will either be parabolas that open up, or they will be parabolas that open down. To have degree 2, these would both have to have x squared of some kind. This would be a positive x squared. This would be a negative x squared. Characteristics, the number of x-intercepts, well, we could possibly have options with the x-intercepts. The way I've drawn this one on top, it doesn't quite actually touch the x-axis. We could have a degree 2 with 0 x-intercepts. I could have drawn it just a little bit closer, and we could have had 1 x-intercept. Or like the one on the bottom, I could have drawn it like that, and we'd have 2. No way to have any more than 2 x-intercepts. The number of y-intercepts, we will always have 1. And the end behavior, looking at the graphs, this one on top starts in quadrant 2 and ends in quadrant 1. The one on the bottom starts in quadrant 3, ends in quadrant 4. Now you might be looking at this one on the bottom and say, well, it doesn't actually hit quadrant 3. Well, it actually does. This is just the small window that we have to look at it. If we were to continue drawing out the left side, it would eventually hit quadrant 3. Degree 3 polynomials. I'll draw these side by side just because that's how I have space. These are essentially lines with blips in the middle. We can move up, left, right. We can move down, left, right. To be a degree 3 polynomial, we have to have x cubed. Moving up, left, right is a positive leading coefficient. Moving down is negative. The number of x-intercepts, well, looking at this, I've drawn the first one has 3 x-intercepts. The second one only has 1. Given that, 2 is a possibility if one of those loops just touches the x-axis. But 0 x-intercepts is not an option. We can only have 1, 2, or 3. The number of y-intercepts, we will always have 1 y-intercept. And the end behavior of a degree 3 is actually the same as the end behavior of a degree 1. We're either going from quadrant 3 into quadrant 1 or from quadrant 2 to quadrant 4. Now you might be looking at this one on the left and saying, well, yes, it does start in quadrant 3, but then it goes into quadrant 2 and back into quadrant 3 and then into 4 and then into 1, which is not false. However, we only care about the far left and the far right, the absolute beginning and ending of the function. So this is why we would just say quadrant 3 to quadrant 1 here.